Okay, I hope you can hear me well. Hi, everyone, and thanks so much for having me. Great workshop so far, thanks to the organizers. So I've entitled my talk, Dislocation and Grain Boundary, Walk into a Bar. And what I was trying to say with that is that we're gonna look at some processes that are occurring really at the microscopic scale. So in particular, we're going to be looking at grains and dislocations and some other crystalline defects. And of course, the reasons we're trying to understand some of this physics that is occurring at the smallest scale is that we're trying to understand how it governs, how it controls or informs us about the macroscopic processes so that are taking place in geological, time, and space scales. Sorry, I'm just trying to arrange my screens here. Here we go. Right, so of course, lithospheric deformation enters a lot of, kind of influences a lot of the processes we care about, from the largest and slowest timescales like plate tectonics and mantle convection to more rapid or kind of human timescale processes like earthquake cycles. That's a form of motivation. And sort of closer to what this workshop is focusing on, is one of, I guess, of more kind of peculiar features that characterizes the lithospheric rocks is that they can undergo shear localization. And a solid that is deforming and may undergo localization typically involves some form of feedback between the rate of deformation and weakening, meaning as you're deforming this rock, it weakens, and then that part that is weakened deforms faster, which makes it weaken even further, and so forth and so on. And there are a number of proposed mechanisms for what may cause this sort of localization in the lithosphere. Some of them, there's been proposals for fluids or presence of other minerals or anisotropy, also a lot of it like we've heard in talks both earlier today and yesterday. So one of those mechanisms are microstructural changes, and in particular, by this I'll mean grain size evolution that I will focus on today. And in order to kind of have changes in the microstructural evolution, even kind of deeper down into the physics of it, involves the formation and motion and kind of dynamics of the crystalline defects. And simply one can think of crystalline defects, they also occur in various scales, and we can think of them as kind of points and lines and planes within crystals, which kind of more formally known as vacancies, dislocations, or grain boundaries. And so, and these crystalline defects, they are not independent, they interact with each other. And some of these interactions, they will then on a larger scale manifest themselves as overall strength or rheology of the rock. So we're gonna look at how these crystalline defects evolve and what they mean for the rheology. Here we go. So first, I'm going to focus on dislocations, and here's why, just to give you some motivation. A lot of the Earth, so within kind of across Earth conditions, a lot of the solid rock deformation occurs by dislocation creep, and that involves formation and motion of dislocations. As the rock deforms, the dislocations that are these linear defects within the crystal, they may cluster and pile up and explain some of the rock hardening that is in particular seen at colder temperatures. The dislocations are also the ones that are responsible for parts of dynamic recrystallization, where they can accumulate and form subgrain boundaries and induce grain size reduction, which then leads to weakening. Presence of so different grains may have different dislocation density, and neighboring grains with different dislocation density can then, it can induce forces, so kind of thermodynamic forces onto a grain boundary, which would then drive the grain with a low dislocation density to replace the grain with a high dislocation density. This just to say that presence of dislocations puts a grain at a higher internal energy. This is sort of analogous to normal grain growth, where smaller grains tend to be replaced by larger grains as they're at a higher internal energy state. And finally, because dislocation kinetics or dislocation processes occur on their own characteristic timescale, they may also be responsible for some of the transient creep that we know we know that the solid rocks are prone to. The sort of transient stage before we reach the steady state rheology. So with this in mind, let's look deeper on what the dislocations do and how they move. And the first thing we're going to look at is the dislocation creep. So when creep of a rock, of a solid rock, is primarily happening through motion of dislocations, we can describe it through what's known as the Orovan's equation, where very simply the strain rate, I hope you can see my mouse when I use that here, where the strain rate at which the rock deforms can be expressed through the dislocation density. I'm going to try to get used to seeing this box I have on the right, where I list some of the most important parameters that will enter the equations I'll be showing. You don't need to remember them all, but they're just here for your reference. Okay, so the strain rate by dislocations is proportional to dislocation density, so just how many of these dislocations you have to move your strain around. The length of the Burgers factor, that is just characteristic of a dislocation of a certain type. And then the velocity at which these dislocations move. And dislocations can move by different processes. So here in detail, I'm showing climb and glide. So each of these processes has their own characteristic time scale that, for your intuition, I'm characterizing with a climber and a glider. Climb is typically slower. And one of the reasons it is slower is that this type of dislocation motion requires diffusion of vacancies across the grain. So this is a diffusion limited process. As with any diffusional process, it becomes more efficient at higher temperatures. And also, just because it's happening slower, when your rock is deforming at slower rate, climb may become increasingly more significant as to how much it contributes to the overall deformation. So this is climb, which is schematically shown here. If you're thinking of dislocation as just kind of a plane of atoms or plane of vacancies shoved into a crystal, climb would just be kind of transferring vacancies to and from that plane in order to have it move out of its slip plane. Okay, and then we have glide, and glide is typically a lot faster, mainly because it does not require any sort of diffusion of material across your crystal. Just kind of this typical here shown for the example of an edge, just hops over this potential wells as it moves along in its glide plane. So this process is faster at high strain rates. For example, typical for experimental strain rates, this may indeed be the dominant deformation mechanism or dominant dislocation motion mechanism. However, glide is sensitive to presence of other dislocations. So as it's trying to move through its plane, encountering other dislocations may slow it down significantly. So this process will may become slower the higher density of dislocations. So that was a qualitative description. Quantitatively, and you don't need to remember those equations, the most important part I want to point out here is that this is our glide velocity. And again, just to emphasize, it is dependent, so it is, both of these processes are thermally activated. Okay, so to move both dislocation, so both in glide or by climb, you need thermal activation of smaller scale defects along the dislocations. However, glide in its plane is strongly stress dependent. And it's not just the applied stress, it's the stress that you're applying to deform the rock, but it is also the effective stress, meaning the applied stress and the stress internal that is due to the presence of other dislocations. So one of the main complications that you have from understanding the kind of physics of dislocations is those long-ranging strain and stresses that presence of a dislocation induces within the crystal. So the effective stress that is driving the glide is a function of some applied stress minus, or typically resistive force from the presence of other dislocation. And again, I want you to get used to this omega symbol that will always stand for dislocation density. And then climb, like I mentioned earlier, is a diffusive process. So it requires diffusion across the grain. And it is typically limited by the slowest diffusing species, which for olivine, one of the main components of the upper mantle and lithosphere, is silica. So climb, which is why one of the reasons climb is slower. So here just showing you an example where I'm plotting the strain rates as dictated by the Orovan's equation. So these velocities times some dislocation density. So the typical strain rate for varying dislocation density. And glide here is shown as a solid line. So as you, at low dislocation densities or relatively low dislocation densities, glide is efficient compared to the climb velocity. So the strain rate will predominantly be accommodated by that. However, once you reach a kind of a high enough dislocation density, glide becomes difficult due to the interactions between different dislocations. And so climb may eventually take over. The main takeaway from this is because the rate at which the rock is deforming when in dislocation creep is dictated by the velocity of the dislocations, the rate at which the dislocation moves and what that rate depends on, whether it's stress, how it depends on temperature, how it depends on presence of other defects or vacancies, will be determined based on the mechanism by which the dislocation moves. All right, and one of the controlling parameters for which of this dislocation motion processes is most important is dependent on dislocation density. So we're gonna look more at what dictates then the dislocation density in a deforming rock. And a kind of a simple, perhaps most common way to look at the evolution of a dislocation density within the rock. One can also think of it as some form of preserving deformation history of a rock is looking at its dislocation density. So we'll be looking at sources, meaning what are the processes that increase the dislocation density or multiply the pre-existing dislocations, and sinks, so processes by which dislocations may annihilate or recover. So for the particular model we chose, and also which is common in a lot of other modeling approaches to model this evolution, we'll look mainly at two dislocation sources that are thought to be dominant for Earth-like conditions and also in olivine. One of them is grain boundaries, so exemplified here as in the work by Ashby from 1970, because grains within a crystal in a polycrystalline material, they're polygons, so when they're trying to move relative to each other, in order to avoid opening any gaps or voids or overlapping, so in other words, to be strain compatible, one of the ways they can be strain compatible is by introducing the dislocations along the grain boundaries. These are termed the geometrically necessary dislocations. So this is one of potential sources close to the grain boundaries for forming and increasing the dislocation density. Another important source is what's called the Frank-Reed sources. And these involve, so this is schematically shown here from well, I'll just explain this quickly. What this requires is two pinning points that pin dislocation at two different ends. And then due to the applied differential stress, that dislocation that is pinned at its ends is trying to bow out. So A and B here are the pinning points. And the applied stress causes the dislocation to bow out, wrap on itself, form a sort of larger dislocation loop that then continues to emanate outward, while in the where the pinning points were, the process restarts again. So by this, you kind of have radiating away dislocation loops and increase your dislocation density. And in a kind of remarkable experiment that came out recently in 2016, Idrissi et al. Actually managed to image what looks like a Frank-Reed source operating in real time in olivine. So I don't know how easily you can see that here, but this is a dislocation loop emanating outwards, possibly by a Frank-Reed source. Quite an achievement because modeling dislocation motion in real time is quite a challenge. For the dislocation sinks, we have grain boundaries. So most simply imagined is as dislocation moves through a grain, by the time it reaches the grain boundary, it's basically absorbed at the grain boundary and its job in accumulating strain is done. So that is one way to annihilate the dislocation. Another dominant or and significant contribution to recovery processes is what's known as dipole annihilation. And this process requires climb of dislocation. What it means is that in a crystal, if you have, for example, two dislocations with opposite sign, and by opposite sign, I mean, again, if you think of them as edge dislocations, and if you think of a dislocation in general, it's just a plane of atoms, of vacancies that are shoved into a grain or crystal. Dislocations of opposite sign would be one plane shoved on the opposite sign than the other. And so the dislocations with opposite sign would then attract each other and eventually merge. But in order to do that, they need to exchange atoms of vacancies, and this would require climb. So this is a climb limited process. Okay, so putting all of these mechanisms together into evolution of a dislocation density, this is shown here. I'll explain to you what these different terms mean. So I explained these four sources and sinks. This is evolution of our dislocation density through time. Here's our sources through grain boundaries. R here stands for some typical grain size. And the reason it scales inversely with grain size is because the efficiency of this source is dependent on how much grain boundary you have. So this is basically your grain boundary density over here. And the rate at which the dislocations can then leave the grain boundary and move away to allow for a new dislocation to form is dictated by the velocity here, which is both glide and climb. Here's the Frank-Reed source. As I said, the Frank-Reed depends on the stress that is applied. Actually, no, I'm sorry. I think I may not have explained that. So in order to bow out the dislocation, there needs to be some minimum amount of stress that is resolved on the plane of that dislocation. And that minimum stress depends on the distance between the pinning points. You can think of it as bowing out the dislocation is kind of like bending a beam, and it's easier the longer the beam is. So there needs to be minimum stress in order to operate this Frank-Reed source. And here, this again, this efficiency of the source scales with stress and with grain size, because the maximum distance between your pinning points of a dislocation that you can have within a crystal is limited by the size of the grain. So you can have a dislocation that's longer than the size of, well, that will bow out, that is longer than the size of the grain. And it depends on the dislocation density as well, just because you need the presence of other dislocations that may act, for example, like pinning points that would hold it in place as it bows out. Grain boundary sinks, again, this is just as dislocation would merge onto a grain boundary that goes as a grain boundary density, and the dipole annihilation. So dipole annihilation depends on the efficiency of climb because it requires exchange of atoms. It strongly depends on dislocation density because it dictates the probability of one dislocation of one sign encountering another dislocation of the opposite sign. And another thing that dictates the probability of them interacting with each other is the lifetime of a dislocation within the grain, which is dictated by how long it takes for a dislocation to traverse that grain in order to interact with the dislocation of an opposite sign. So this is where the dependence of grain size comes in there. So this entire equation is then plotted here. So I'm showing you the rate at which the dislocation density increases or decreases through time as a function of dislocation density itself. And I'm plotting it for different grain sizes. So what you see here, I'll first explain this grain line, which is the field boundary grain size. Field boundary meaning that at this grain size, the grain line, the strain rate that is accommodated by dislocation creep is as efficient as the strain rate accommodated by diffusion creep. So if you're a grain whose size is much or larger than this, you are predominantly deforming by dislocation creep. So when you're predominantly deforming by dislocation creep, you'll be here, and you'll notice that this equation, this omega dot, has a steady state. So this is where these curves cross the zero line. And for grains that are close or larger than this field boundary, there is only one steady state, and it hits, so this is this black line here where omega dot crosses zero. So the steady state dislocation density, which would be your dislocation density if you go out and you observe a rock and you assume it's a steady state. This will be the dislocation density you expect to find. Seems to not have any dependence on grain size, but it does depend on stress. And this has actually been inferred theoretically previously and is also robustly observed in laboratory studies, to note again, deforming at relatively high strain rates, and sometimes also called the temperatures. This empirical relation with dislocation density is entirely dictated by stress to some power. Here I'm only showing Gauss stress squared, is independent of grain sizes. However, once the grain size is relatively small, where these terms that I've delineated before that depend on grain size become more dominant or more significant, there is, in addition to this steady state that is close to the one for larger grains, you also have a new steady state that is also that the system may tend towards. So another steady state dislocation density that you may see in a finer grained material. This result is easier shown in this plot here, where I'm just plotting the steady state dislocation density versus grain size. So this is the same plot as I showed you previously, but now versus grain size. So again, the grain line is the field boundary. These two lines are grain sizes that are larger than the field boundary. And as you can see, the only steady state dislocation density they have available is this value that is the same as what is experimentally predicted and predicted by some other theoretical models of steady state dislocations. However, once your grain size falls below a certain size, that certain size being the field boundary, for example, there's a possibility for another steady state. And so if your grain is growing from a dislocation poor state, the first steady state that we'll encounter, and which will be stable, is a much lower dislocation density. So what the takeaway message from here is that taking into account various sources and sinks for dislocations, the dependence of the steady state dislocation density may not only be on stress, as you would see for larger grains or materials deforming predominantly dislocation creep, but may also have a dependence on grain size for finer grain material. And those steady states would be at a smaller dislocation density. Okay, that concludes the first part of my talk. Let me keep track of time. Sorry, how much time do I have?
You will need to round off, Elvira.
Oh, sorry. Okay. Okay, I'll go through. Wow, that that got away from me fast. Let me very quickly get you to. I'll make a decision here. Okay, so as we go from strong coarse grain material to weak fine grain material, I've shown you before that we wanted to look at interactions of dislocations and grain sizes. And so in another theoretical model, we had evolution of grain sizes and dislocation density simultaneously. And I'll just go through this fast. You don't need to. The most important part of these equations is, sorry, here. So when we put together a theoretical model for evolving grain size as driven by surface tension as a normal grain growth, and by contrast and dislocation densities by processes I explained earlier. And we have evolution of dislocation density. This is just a simplified version of the equation I showed you before. We see a quite rich behavior that the system may tend towards, characterized by, so this is a steady state, microstructural steady state that the system may evolve towards, which can include, I'll show you here. If you start off time on the x-axis with some ensemble of grains, and you look at where this ensemble of grains goes towards microstructurally, it may undergo something that is similar to a steady state. So it starts off, for example, unstable here. This would be your normal grain growth, and eventually move towards a steady state after gobbling up some of your smallest grains. And I'll just move you towards here. Another, if you start off with a kind of heterogeneous or some sort of distribution of grain sizes that are unstable, and when the kinetics of dislocations and the kinetics of grain boundary motion are such that the rate at which the dislocations can adjust to the changing grain size is relatively slow, you may have overshoots and undershoots as the system moves towards a steady state. So what this means is that in the transient stage of your material deformation, the material may weaken and harden, and your dislocation density and grain size may increase and decrease through time at some characteristic time scale. And what this, one of the things that we looked at the implications for this transient unstable rheology that will eventually move towards a steady state is what kind of effects it has on the post-seismic creep. So how it dictates the viscous relaxation after an earthquake event. So the model for that is shown here, where some of the elastic energy that is stored in the crust following unlocking of the fault, the shallow portion of here kind of visualized for a transform fault, when the shallow portion of the fault slips, the deeper portion of the plate may be impeded from moving by the underlying viscous mantle or ductile lithosphere. And so the rate at which the entire plate relaxes is dictated by the viscosity of this deeper layer. And the viscosity of this deeper layer itself is then a function of the microstructure like grain size, and is also a function of stress, because here the material can deform by diffusion and dislocation creep. And so we've coupled this kind of very simple geodynamic model with our theoretical model for the evolution of grain size and dislocation density. And we've looked, given the different scenarios for how the microstructure can move towards a steady state, we've looked at what sort of different relaxation scenarios the system may see. And I'll only show you two examples here. So in case where the parameters that dictate this coupling between, so within this regime diagram that tells you how grain size evolution and dislocation density evolution are coupled, if you're in this region that is kind of a stable equilibrium, it behaves very much just like isoviscous case, where here on the x-axis is time and on the y-axis is grain size and stress. So grain size can evolve towards its steady state equilibrium relatively quickly. And so the stress will just drop off exponentially as you would expect in an isoviscous material. In another case where you have this coupling of dislocation kinetics and the rate at which the grain boundary moves in response to the evolving dislocation density, you can have this case where the grain growth is non-monotonic through time, and the mean grain size can increase and decrease through time on a time scale of a few decades or say hundreds of years. And the associated evolution of stress will also be different, where initially the stress may decay much faster, but after some time, as the grain size increases, will actually flatten out and decrease a lot slower than you would expect in sort of more simplified model of microstructural evolution. So this is just one kind of simple application example for how varying time scale of microstructural processes may manifest itself in the time-dependent relaxation rate of viscous materials. Again, something we may look for in, say, geodetic data of post-seismic strains. So with this is the final slide of my talk. What I was trying to show you is some of the recent models we've been working on kind of physical processes that control the strength and the creep behavior of rocks, and predominantly ductile rocks. We focused on the dislocations. And of course, the main motivation for these models is to inform the larger scale model so that we don't necessarily need to kind of model all the itsy-bitsy details of vacancies and dislocations and grain boundaries, but given a better physical understanding, we can build better parametrizations of these models that can then enter the larger scale geodynamic models to be more as physically consistent as is practical. Thank you for your time.
Thanks a lot, Elvira. We're running a bit out of time, but we have scheduled a slightly longer break now than we had yesterday. So I would say we take a question. And there is one from Saga Musati in the chat. It says, great talk, thank you so much. So in post-seismic phase, the deformation is usually dominated by dislocation creep and is independent of grain size. So how do you explain this using your grain size dependent model?
I'm sorry, I was lost. I'm just, is that question in the chat? Oh, here. Yes. Independent, right. So I've tried to look at some of the models that look at the kind of evolution of strength, or I guess what is the creep regime, whether it's diffusion creep or dislocation creep, could be grain boundary sliding and different regimes. And of course, we're dealing with the polycrystalline material. So what the dominant deformation mechanism of the deeper layers of the plate, I believe remains kind of a subject for investigation. I think one could envision that there will be portions that are predominantly deforming by dislocation creep and portions that may be fine-grained or at a different stress that would put them in a different rheological regime. I think one of the particular observations I can think of that argues that deformation in post-seismic zones is by dislocation creep is the observation of seismic anisotropy. But I think interpretation of those seismic data, again, is still a subject of discussion. So certainly dislocation creep is an important process. Grain size dependence can manifest itself in many different ways. I don't know if that clearly answers that, but.
It's complicated, I guess. So we take one more question from Marcel Thielman. Which is about the grain growth due to both surface energy rejection and the dislocation density differences. So is there a critical grain size where one process dominates over the other?
So that's a great question. That is exactly what we were trying, and I'm sorry I had to skip so quickly over those, that theoretical explanation. So where so mainly we're looking at this two, like you said, dominant forces, which is surface tension and the contrast in dislocation density. And there is both a critical grain size that would, you can think of it as there is a steady state grain size at which the surface tension contrast and the dislocation density contrast would just balance each other. So a steady state and a microstructural steady state in such a system is possible because of the offsetting effect of these two forces. What that critical grain size is then dictated by the deformation history of the grains, the stress, temperature, and kind of other. In our model, once we've non-dimensionalized that, we have two governing parameters, which is alpha and beta. And alpha stands for how much force is exerted on the grain boundary for a given dislocation contrast. And beta tells you how fast are the dislocation kinetics, so how quickly dislocation density can adjust to changing grain size. So predominantly these two parameters will tell you what's your critical steady state grain size. That was that pastel colored regime diagram I showed that I skimmed over, sorry about that.
Thanks a lot.